Stephen Swallen. I teach some of the chemistry courses on campus, and I had the pleasure of leading the honors presentation, or the honors group, for Chemistry 155. We were a large group, about 10 students who spent the entire semester working really hard looking at energy and alternative energy sources and how energy can be derived from various sources, how it applies to our society. And so the students really took off looking into different alternative energy sources, how they are produced, but a lot more than that, actually looking into things like economics and politics and culture and ecology and really the big impacts of energy. And so our student group will be able to tell you all about different energy sources and alternative sources and how that might impact our world. And so interestingly, we actually did this as a sort of a graduate seminar technique where we all met on a weekly basis and the students did good research. They got skills in looking up information in the literature, and then they would come each week and tell us about the things that they had learned. And so they got good practice with both doing research and scientific presentation. So I would like to introduce our Chemistry 155 honors group, and I will introduce each of the students. You guys can come on up. Caleb Brey, Jarrett Schnaare, La Yang, Patrick Koss, Rick Kreutzmann, Eric Tisil, Jessica Duran, Nick Kolar, Samantha Mueller, and Stephanie Siebers. So we have our group.
Hello, everyone. For starters, I'll have you take a look at this picture here. This is an image of Shanghai, China, 1985. And this is as it appears today. Shanghai, like most cities, has and will continue to undergo rapid developments due to increased population and economic growth, the extent of which is made possible by an ever-increasing consumption of energy. The global demand for fossil fuels is projected to increase by 56% within the next 30 years, leading to increased carbon emissions, damaging human health and the environment, and will increase competition for this non-renewable and limited resource that has been so vital for sustaining modern human activity.
America and energy have a long history, as well as energy in the world. On this graph, you can see that relationship. On the x-axis, you can see the years, and on the y-axis, you can see energy consumed by America in BTUs, which stands for British Thermal Units. A British thermal unit is the energy it takes to heat 1 pound of water by 1 degree Fahrenheit at 1 atmosphere, or 1,060 kilojoules. America's first energy was wood, and that was from 1775 to 1883. At 1883, biomass and combustible fuels were at equilibrium, and then in 1883, coal was the leading energy source. In the 1950s to 1980, the U.S. population slowed, and we started importing energy. So where does this leave renewable energies? If you look at the yellow line, you can see renewable energies. In 2010, solar and wind and other renewable energies started looking more viable, and they passed nuclear. From the graph, you can see that petroleum, natural gas, coal, and other combustible energies are leading in America. The byproducts of this are carbon dioxide, sulfur dioxide, methane, and nitrous oxide, which are all deadly to humans. So I leave it to you. Investing in energies and consume is how these energies become the leading energies in America.
Politics is probably one of the largest impacts and decisions on which of our resources we end up using. As you can see from this graph, Wisconsin has been leading in coal production, or not production, but the use of coal for energy. And a lot of those decisions are based on our politics, and policies that come from politics based on energies. For Wisconsin, most of that coal ends up being used for electricity. And most of the other renewable sources that we have available to us are just either getting glanced over or just not having enough emphasis put on them. Private sectors and private businesses can only take things so far, and a lot of government backing is needed to have our resources available to us when all of the petroleum and coal runs out. And with that, we can begin exploring some of the options we've been researching for the past few months. Various options that we'll be discussing.
Okay, so my part of the research was on ethanol. Ethanol is an alcohol-based fuel, which is made by fermenting the sugar and starch components of plants. Materials that we currently use are made from corn and sugarcane. We currently use mixtures in flex fuel vehicles. It's known as E85. It is 85% ethanol and 15% gasoline. Okay, so the advantages and disadvantages of ethanol. It is domestically produced, so it would reduce foreign imports that we currently use for importing certain things like gasoline, as well as we would reduce emissions. If all cars were E85, we'd save about 30 million tons of CO2 per year. Some cons, limited availability, both in fill-up stations, so we currently don't have E85 at every gasoline station, as well as there's limited land availability. Last year we used 27.2 million acres to produce the mixture ethanol, and that's not with every car running on E85. So if there's limited land availability, that means that there will be an increase in food prices. And ethanol really isn't a great future because you're still combining gasoline and another product. It's just a temporary solution, not a permanent.
Butanol, a lot like ethanol, is an alcohol-based fuel that is also mixed with gasoline. It can be produced through fermentation, like beer, or conversion of ethanol through catalytic conversions and processes. It does reduce fossil fuel use dependency because you're mixing fuel with the alcohol, so you don't need as much fossil fuel. Ethanol can usually be mixed to a maximum of 15%, whereas with butanol, in lab setting conditions, it can be mixed 85% into gasoline, meaning that only about 15% of your fuel will contain gasoline. The problem is only about 12% is considered legal, and the process of making the butanol tends to be quite a bit more pricey and lacks more practicality.
Another type of biofuel comes from algae. We can actually remove oil from algae and refine it to be used as fuel, and half of their weight is actually lipid oil. There are 3 different methods that can be used to remove the oil. There's the oil press, which is the most common, and that removes 75% of the lipid oil. There's hexane solvents, which is a little more difficult to remove the oil, but it does get 95%. And supercritical fluids, which turn 100% of the oil into, or 100% of the algae into the oil. There's also 3 growing methods. There's open pond growing, vertical growth, and closed tank bioreactor. So why is algae biofuel a viable option? Algae biofuel burns cleaner and more efficiently than petroleum. Pressed algae remains can be used as both fertilizer and feedstock for farm animals. It can also reduce life cycle of CO2 emissions by 50 to 70%, and the price per gallon will be approximately $2 to $3. It can also be placed near energy manufacturing plants to reduce CO2 emissions. So all the smoke that's coming out can just be run through algae, and they soak up all the CO2. Some drawbacks to algae biofuel: it's still in the experimental phase, so more funding needs to go into it, and it's not yet engine compatible. So the picture on the left is a bioreactor system that's used to grow algae, and on the right we see an oil press, and you can kind of see the oil kind of oozing out of that.
So nuclear fusion is the process of combining two atomic nuclei into one larger nucleus. The graph and the chemical equations are showing us what's happening now. It is the process how the sun creates the huge amount of energy. The reaction starts with protons at very, very high temperature and pressure and ends with helium. And at each step, there is huge amount of energy released. We want this to happen on the Earth, so we can get the huge amount of energy rapidly.
We're interested in fusion because hydrogen is the most common element in the universe, so fusion would provide cheap, essentially limitless energy. It produces little to no waste to doing so, and it would be a lot safer than current nuclear power methods. Unfortunately, as of today, it's nowhere close to being viable. The conditions that are needed for fusion to be sustained are very hard to achieve, and even with hundreds of millions of dollars a year being put into research, availability on a commercial scale isn't expected until 2050 at the earliest.
Okay, hydrogen, as already mentioned, it is the most abundant element in the universe. There's just one catch. In nature, hydrogen is not found isolated. It's usually bonded to either an oxygen or carbon atom in another molecule, and we have to extract it first before we produce a pure product. So hydrogen has the highest energy density of all fuels, nearly 3 times greater than gasoline by mass, not volume, which means bigger and bulkier storage. I'll explain how the fuel cell works here. What you have is an anode on this end, cathode on this end. You have electrolyte in between. As hydrogen moves from the tank, it reacts with a catalyst. It's a platinum catalyst. What happens is that a proton, positive charged molecule, and red bullets, moves through the electrolyte. You have an electron, negatively charged molecule, particle moving through a circuit here, producing electric current, and both of them, those particles meet up, reacting with oxygen on the side, and what ends up leaving the system as exhaust is just H2O and water and heat. Now I should mention catalysts, they are platinum, and there would be multiple numbers of catalysts for these fuel cells because they have to be stacked up. Each fuel cell here is about 0.7 volts. That's about enough volts to power a light bulb. So we can use this to generate electricity to power a car, or we can also use it to, let's say, what businesses like eBay and Google are doing is powering their servers, for example, fuel cells. So hydrogen does have some advantages. It can be produced domestically by many different sustainable methods such as solar, wind, or even geothermal energy. When using a fuel cell, hydrogen produces no harmful emissions. Hydrogen must first be compressed and even cryogenically frozen to its liquid state before storing and distributing. This process, of course, consumes plenty of energy in of itself. The infrastructure to produce and distribute hydrogen would cost hundreds of billions of dollars.
Solar energy is already a very popular alternative energy source today. Our campus actually has a couple of solar cells. Solar energy is 100% renewable. A solar cell consists of 2 silicon layers, one positively charged silicon layer and one negatively charged silicon layer. When a photon comes from space and hits a solar cell, it disrupts the positive-negative equilibrium and creates creates an electric charge, which powers stuff like light bulbs and stuff like that. The typical solar cell lasts about 20 years, so it'll last a very long time. Solar energy has very little byproducts when it makes energy. The only thing bad is that when solar cells are made, a few bad like elements are used to dope the silicon cells to positively charge them or negatively charge them, but it's not as bad as just trillions of pounds of CO2 being let off by cars and stuff. Once the solar panel is set up, the energy is free. Solar cells can be placed anywhere with sunlight, and they can just generate electricity instantaneously when light hits them. However, solar cells, they have very low energy output. The typical solar cell is only about 14 to 18% effective at generating electricity, and that means that only 14 to 18% of the energy that it receives, it'll create energy with. No energy is created at night without sunlight. However, there is some technology that's being created today, such as infrared solar technology, which actually is making energy out of infrared energy that's released from the sun, which I think is pretty cool. So instead of just making solar energy during the daytime, we can actually generate electricity at nighttime. So, however, they also need to be maintained. Like, you can't get solar energy with a whole bunch of dust on top of the solar cells, otherwise nothing will happen.
So we've talked about all these alternative energy sources, but one problem that they all face is how do we store this energy? And one thing I looked at was alternative battery types, and one in particular was a sugar battery. And what they did with this is they took the biological process of termites digesting wood to get their energy and try to use the same enzymes to digest wood, or to use with sugar to get raw energy. This technology is very useful because it would eliminate many of the toxic waste products that are associated with constructing modern types of batteries. The downside to this technology is it's only in the early research phase, and much more research will be needed to be done, and a lot of money will have to be raised to try to get this to a point where we could use it in our everyday lives. It is expected that a AAA or like a AA battery that is a sugar cell or a sugar battery, and then a AA that is a regular alkaline, the sugar battery will last twice as long as the alkaline battery. And then to recharge this battery, all you would have to do is add more sugar.
Along with sugar batteries, another alternative design for batteries is the flow cell battery. This is very similar to the hydrogen fuel cells in that it has an analyte and a catholyte, and they react together to create a charge. However, there are different compounds within the tanks. The tanks are full of compounds such as lithium ions, quinones, which are organic, metal-free compounds, and then scientists are looking at a bunch of different compounds besides those. In the membrane, which is the center over there, there's an oxidation and reduction occurs, and it creates a charge which can power whatever you're trying to power. Scientists have found that semi-solid slurries work the best as opposed to liquid compounds. With this design, you have the option of replacing the compound whenever it runs out. So if you're using it for an electric car, it would be just like refueling the car, and you'd have a completely new battery, which is nice for that application. It also separates the energy from the circuit, which avoids a lot of different electronic things that you can't do with a normal battery, like keeps energy from depleting. However, one of the cons is that it's very bulky and it would be very hard to make for smaller applications.
So to start out with, the average Wisconsinite already pays about 12.5% more money on their energy than the entire United States does on average. Now that's a lot of money. It's continually rising about, seems to be going about 1% each year, which is really insane. If you do a calculation, in about 100 years it will double. And even, I'll actually talk about that more when I get to dropping oil supply. But anyways, the average Wisconsinite owes about 10.37 cents per kilowatt hour compared to all these other states here. And it's, even though it doesn't really look like much, it is a lot of money already. You have to understand that we have to pay bills. We have to pay, we have to pay for college, and look at all this. 10.37 cents, guys. What's worse, though, is that all of our energy that's being used to generate all this, all the oil, it's going away. All of it. All of it's going to be gone in 40 years. And finding an alternative energy to fuel all this is not something that we want to do, but something that we absolutely need to do. Not only is oil going to completely just go away in 40 years, but the demand is going to go up as the population of the entire world doubles, quadruples, and there's going to be no oil left, and nothing's going to power the world to continue to go out into outer space or do cool stuff like that. So it's bad, guys.
So this graph tells us how CO2 emissions would decrease if we increased the amount of renewable energy that we'd be using. So the very top black line represents a 0% increase in renewable energy, and every other line represents an increase. So if we increase renewable energy by 50%, we could cut down CO2 emissions almost in half by 2050.